Hello Chem 1B, this is chapter 22, lecture video 6, and we're going to begin talking about crystal field theory. This is the topic that we'll probably be discussing for the rest of this chapter. So what crystal field theory seeks to do is to describe how coordination compounds are existing in terms of their quantum structure. In addition, it allows us to predict properties such as magnetism, whether a compound is paramagnetic or diamagnetic. And it all revolves around the d orbitals in our metal ions that are in the coordination compounds. Now, from Chem 1A, if you remember some of the quantum mechanics we learned, any time we have d orbitals, we have 5 of them, right? And these 5 lines represent those 5 d orbitals. Each one of those d orbitals has a different ml value. Now, when the transition metal ion is just by itself, there's nothing attached to it, no coordination covalent bonds attached. The d orbitals are what we call degenerate, or in other words, at the same energy. When all 5 d orbitals are at equal energy, we call that degenerate. However, when we bring an electric field into the area that we have these d orbitals, they no longer are degenerate. They're no longer at equal energy. An electric field will actually cause the d orbitals to increase in energy, and some of them will increase more than the others. For instance, when you have the d orbitals in an electric field, the 5 d orbitals that were all at the same energy, once we put them in an electric field, shift to a higher energy. Now you notice these 3 all shift to equal energies, much higher still, but they're all equal to each other, and these 2 d orbitals go up even higher. This is the shift for an octahedral. And so in an octahedral, we have these 3 lower energy d orbitals, and we have these 2 higher energy d orbitals that shift up even higher than the other 3. Now, why do these shifts happen? Well, because by putting in a ligand, we've actually moved these d orbitals into an electric field. Because remember, when we form a coordinate covalent bond, we're sharing 2 lone pairs of electrons. And electrons have electric fields, because that's kind of how an electric field is generated, through movement of electrons. And if we're donating these electrons in, they're going to be moving around. They're not static. So it's creating an electric field around the d orbitals, which pushes them up to different places. So again, the electric field here in this case comes from the lone pair of electrons that are on the ligands. These electrons create an electric field and therefore split these d orbitals. Now, depending on what shape or what structure our coordination compound has, octahedral, square planar, trigonal, or tetrahedral, or linear, our splitting is going to look different. And we'll talk about why on the next couple slides. But this is the first intro to what we call crystal field theory. So the arrangement of d orbitals really determines the splitting energy levels. And these are our 5 different d orbital shapes, right? So when we talk about in Chem 1A, usually I only show this guy, or I mean this guy, either one. They're only slightly different from each other. And it kind of looks like a clover is what I say, but there's actually 5 different orientations of the d orbital, and one that looks kind of funky. This is called the dz squared because it's along the z-axis. Here's our z-axis in 3-dimensional space. And I don't really need you to know these names per se, but it's important to kind of look at the shapes and see how they're different, right? In this one, our lobes are in between our axes, right? So here's the x and y axis, and here's the we'll use a different color. Here's a z axis, right? And you can see that all of our d orbital lobes are in between each of the x and y axis here, right? And the difference between this guy and this guy is over here. You can kind of see that all the d orbitals are along the x and y axis, right? They're directly on the axis. So they look very similar, but they're just shifted in orientation just a little bit. So when we bring these lone pairs of electrons into the structure, like here with our Cn minus, it creates these d orbitals to shift to higher energies. And the more close they are to the electric field, i.e. the ligands, the higher the energy they're going to be at. For instance, if we look at the octahedral, this is an octahedral shape here, our hexacyanoiron, or ferrate 2, is the name of that coordination ion, or complex ion. If you look at the orbitals that are actually higher energy, it's the dz squared and the dx squared minus y squared. And if we look at y, what's happening is these guys are along the bonding axis. All right? So these orbitals are right there along the bonding axis, which means they're going to be more affected by the electrons being closer to them, right? Because the electric field is going to be more potent for these two orbitals. Whereas these guys are going to be close to the orbitals, but not as close as the other two, and they're pretty much all equally different from the bonding areas here with these three. So they shift higher energy still, but not nearly as high of an energy as these two. These guys are both along the X, Y, and Z axis, which is where our bonding is occurring, whereas these guys are not on that axis. These guys are lying in between bonds, which means they still feel the electric field, but just not as strongly as the two orbitals that got shifted to higher energy here. Now, at the end of the day, you really just need to know that we have 3 down here and 2 up here for the shift for an octahedral. I don't really need you to know the labels per se. But if I showed you a picture like of these 5 and I asked you, hey, which orbitals are probably these 2? You should hopefully be able to pick these 2 because they're along the bonding axis. So you should kind of know the theory behind it. But at the end of the day, I don't need you to know that this is dyz, this is dxz, and this is dxy. That's not super important to me. All right, so let's go a little bit more into this. So how much shift occurs here depends on the strength of our electric field that the ligand is generating, right? So some ligands create stronger electric fields than others. Not all electric fields created by our ligands are the same. And so this is really starting to get to the basis of crystal field theory, field relating to the electric field. This delta symbol here, delta O specifically, is the splitting energy for an octahedral, O being the octahedral. It's defined as the distance between these two orbitals up high and the 3 orbitals down below. Now, we have generally different ligand field strength, right? So the electric field strength around our ligands, not equal. Some of them have much stronger electric fields than others. Now, I will provide this series here on your test. You don't need to memorize this. But we do need to know what strong field versus weak field means. Strong field being strong electric field and weak field being weak electric field. And as we go from like CO to I minus, this bit, the delta O, the crystal field splitting energy, decreases. It gets smaller and smaller because this distance is really a basis of how strong that electric field is. The weaker the electric field, the smaller the gap between the 2 orbitals up top and the 3 orbitals down below. Now, all this is great. We don't ever really need to necessarily calculate delta O. You're just going to kind of do this based on where you are here on this series here, and I'll provide this on the test in your equation bank. Strong field ligands are going to split these energy levels, or the orbital energy levels, more than weak field, and that's basically what I said a couple seconds ago.